Hello everyone, Dr. Bennett here, and welcome to the final video in this little mini series looking at airplane takeoff and landing modeling. So in this last little part, we're going to consider the event of a rejected takeoff. And so this is the situation which primarily drives a lot of the regulations in terms of whether you're legally allowed to fly in and out of a certain airport that has a specific runway distance, right? So this is an emergency situation where essentially we assume the worst case scenario. So we're going to assume that our airplane starts here at one end of the runway, stationary, vehicle 0, and then we are going to accelerate along the runway up to the point where we're just about to take off, and at this very specific point, right, where we've reached the takeoff speed, we're going to assume that right there we're going to have an emergency engine failure. So from there we're going to have to abort the takeoff and decelerate in the remaining runway distance. So what's built into this model is a 3-second pilot reaction time right here, and then a deceleration all the way back to 0. So what's going to drive the FAA regulations here in the US or EASA regulations in Europe is the total distance required for this entire thing. And assuming that we can show that our airplane is able to start stationary, accelerate to the takeoff speed, build in this 3-second buffer, and then decelerate from that speed all the way back to 0 within the given runway length, will determine whether we are legally allowed to fly in and out of that airport. So we've seen in the previous couple of videos, the first one we derived the takeoff distance, STO. So we already have that expression for that piece. Right here, our 3-second pilot reaction time, well, we're traveling at the takeoff speed for 3 seconds, so the distance there, just using speed equals distance over time, right? Distance equals time times speed. So this right here will just be 3 multiplied by VTO to give us that distance. But over here we have a little bit of a problem, because in our landing model we assumed that the landing speed was 30% higher than the stall speed to give us a little bit more margin over the stall than the takeoff speed, which was assumed to be 1.2 times the stall speed, so 20% higher than the stall speed to take off. So there's a bit of a disconnect there with the two speeds. So we have to revisit our landing distance equation and replace the assumption of 1.3 times the stall speed as our landing speed to 1.2 to make this the two speeds match at either ends of this this piece right here. So essentially all that changes is this factor in the numerator. So whereas it was 1.69 times the landing weight squared in the numerator before, we're now replacing that with 1.44 times the takeoff distance squared. So 1.44 because, well, we're now assuming that we're 1.2 times the stall speed instead of 1.3, and 1.2 squared is 1.44 instead of 1.3 squared, which is 1.69. So that goes there. And then because, well, because we've burnt an insignificant amount of fuel, right, we're assuming that our landing weight is the same as our takeoff weight, so replace that into there. Everything else in the denominator is the same. So what we have to do in order to calculate the total distance required here is add this to this to this. Add those 3 pieces together to get a total distance required, and that's what this is down here. So this is our takeoff distance from before. Let me show you the equation from where we modeled it in the first video. So that's this takeoff distance, that's that piece. Then here is our 3 times the takeoff speed. So that came from, again, from the first video where we assumed this. So that's that piece, 3 seconds multiplied by that. And then the last piece is our modified landing distance equation, which is just a modified version. So in the second video, we derived this expression for the landing distance. All we've done is just modified it for our assumption that we're landing at that we're at 1.2 times the stall speed at this instance right here instead. So replaced 1.3 WL here with 1.2 WTO to get this. And ultimately, that total distance, once we calculate it, will determine whether we are legally allowed to land or legally allowed to take off from a specific airport, because this assumes the worst case scenario where we have an engine failure or an emergency at the worst possible moment, right? Just about where we're gonna become airborne. So there we go. That completes this little mini series on airplane takeoff and landing modeling, and I'll see you soon.